So my goal in this video is to try to explain special relativity. And obviously, I think explaining or teaching in general is somewhat subjective to the teacher. So you're going to have to take me with a grain of salt, I guess, on some of the things I say. But if you watched my video series, we've done the mathematics, we've done the derivation. We can show where we can get. These are the Lorentz transformations. We can show the Lorentz transformations using a thought experiment that we talked about at length in my video series. So I guess the point of this video is to say, how do we get from this thought experiment? And just to go over it again, this thought experiment is very simple. You have some box that travels at a constant speed v in the positive x direction. And at one point in time, at t0, we fire a photon from an emitter on one side of the box. And then at T1, that photon reflects off the other side of the box. And then we'll call this at T2, the photon has returned to a detector. And what we do is we measure the delta T. Okay, so we measure the delta T of these interactions. And really all we can measure is delta TA plus delta TB. Okay, so the thought experiment says if you are an observer inside the box, you're going to observe delta T's with these primed symbols. And if you're outside the box, let's do outside blue, and you're able to measure those delta T's, assuming you have access to that information, so on and so forth, then your delta T's will look like these. Okay, so this is what the thought experiment says, and this is how I've chunked up the three time moments in time, T0, T1, and T2. So my question is, now that we've developed these Lorentz transformations, we apply them as coordinate transformations. So you take some system that's moving at some speed v, and you can do a translation of what an observer inside would see the coordinates as, and what an observer outside would see the coordinates as. And we see this manifest in terms of length contraction and time dilation. So what does it really mean? Well, what I think it means is that we are using photons. We're using photons as a measuring stick for time. I think that special relativity is an example. It's a case study of how time may be represented in terms of space. We know that, like, for example, one of the equations we pulled out was x prime equals ct prime. This is a fundamental statement about how time and space are related through this constant for that reference frame. Okay, and we've shown that for other reference frames, it's not so simple. Like, look at this equation. In terms of the stationary reference frame variables, in this case t, the equation is now more complicated, and it's a more complicated function of speed. So we've used photons as our measuring stick, and furthermore, what we can really say, like one thing you can do mathematically, and you kind of get into this in tensor calculus, but imagine if you said let x4 equal jct, okay, where also we have the definitions that x1 equals x, x2 equals y, x3 equals z. Okay, so we also have those definitions. Then what you can show, maybe I'll do this in a separate video, but you can show that there's an invariant quantity. So if you take x squared plus y squared plus z squared, and then subtract ct squared, in any reference frame, this is an invariant element. Okay, and basically to compute this in the transformed reference frame, by the way, just with their other notation there, this guy would actually look like x, let's use subscript, not superscript. Just make our lives a little bit easier for notation reasons. Okay, x1, x2, x3. You can actually represent this as, say, x1 squared plus x2 squared plus x3 squared plus x4 squared. Okay, well, that looks a heck of a lot like the norm of a four-dimensional vector in space. Okay, so if I runs 1 to 4, and you get xi squared equals 0. So what you can do, and like I said, I won't do the math here, but you can show that if you take x prime squared plus y prime squared plus z prime squared minus ct prime squared, it will be invariant. It will actually yield. It will actually be not only equal to 0, but exactly equal to this. Exactly equal to that first thing we found with reference to the stationary reference frame. So this is an example. I say that special relativity is an example. This is an example of invariance between two reference frames, a relativistic and a non-relativistic reference frame. When you generalize this theory, and of course everyone talks about the general theory of relativity, I like to think about the fact that we used special relativity as an example to show, look, you can create a thought experiment, create a line of reasoning that derives the Lorentz transformations, and you can show that the magnitude of the norm of this four-dimensional space-time vector, or space-time, dimensionality 4, the norm of that is invariant with respect to those transformations. So that's really what we can say about it. And general theory of relativity really gets into the sort of abstract mathematics of that type of invariance. So I feel like I kind of got away from my message here a little bit. I guess the point is that you take a thought experiment like this and you work it out to its end and you get a mathematical result. You recall, or you have to remember, that it's only as good as the thought experiment is itself. So this is why special relativity doesn't explain the general theory or gravitation, for example. It's limited to non-accelerating reference frames. So, but what it does for us, it sort of pulls back the curtain a little bit and reveals a little bit of nature in this sort of invariance that I've described here.